So what are the potential challenges and pitfalls associated with applying correlational coefficients? What are the rakes that we can step on when we perform correlation analysis? And these potential problems are not only important for particularly correlation coefficients, but they often challenge the data based on correlational designs. Even if you apply a more complex statistical model such as regression or something else, moderation, mediation, you still suffer from the possibility of the same potential problems. That's why you need to be aware of them, and that's why we are going to discuss those 5 problems in some details during the next 15 minutes or so. The first problem is the problem of multiple comparisons. It is also called the dead salmon problem. It is based on a famous paper. This label is based on a famous paper by Craig Bennett and colleagues. They basically bought a salmon. They put salmon in an fMRI scanner, and they performed with this salmon the same bunch of tests that they would perform with a human subject within an fMRI scanner. And what is fMRI scanning? Basically, you put some kind of person or object with a brain into the machine, and you compare the activation of different areas of the brain across different conditions. And they had 2 conditions, and the number of potential points in the brain that can be activated, that can be measured, is very high, because the resolution of the scanner is very high. So in this study, they compared 130,000 different points. And they found, using this dead salmon, that there were statistically significant differences between the activation levels in those areas of the brain, in several areas, under several conditions. The only problem was that the salmon was already dead. So obviously its brain could not be activated, and if we don't believe in an afterlife, there is a much more simple explanation. Why did they get those statistically significant differences? Because they used statistical significance level of 0.05 as a cutoff. If you remember, statistically, the level of statistical significance of 0.05 indicates that the chance of getting this effect, this association, or this difference just by chance alone, assuming there is no association or there is no difference in the general population, is 1 in 20. But if you test very many hypotheses, for example, if you test very many correlations, you are likely to get some of those differences or some of those associations by chance alone. This type of error is called a false positive. There is no association in the general population, but if you test very many correlations and your chances of getting a false positive are 1 in 20, eventually you will get it. Here on this graph, you can see the association between the number of hypotheses you test and your chances of getting at least one statistically significant result by chance alone. So if you are testing more than 30 or 40 correlation coefficients, your chances of getting at least one correlation statistically significant just by chance approach 1. They are very, very high. And this explains why students love correlation analysis so much. If you have 10 different variables and you correlate them all among themselves, you get something like almost 50 correlation coefficients. And obviously your chances of getting at least something correlated by chance alone you're almost guaranteed to get some result. You will get something to interpret in your thesis, even if this association is completely spurious and it's a completely statistical artifact. There is no way to prove otherwise. That's why this practice is a bit problematic. If you correlate a whole bunch of variables and you have no a priori hypothesis, and you test very many of those hypotheses, you suffer a substantial chance of false positives. That's why in serious papers that we publish, reviewers typically require us to use either a more strict significance level cutoff, like p less than 0.01, to reduce the chance of getting false positives. Or we use some kind of a multiple comparisons correction, when we adjust our criterion of statistical significance based on the number of hypotheses that we test. And there are different ways to make this adjustment. There is no single one that is perfect. And unfortunately, both of these solutions are not ideal, because if you use a more strict cutoff for the level of significance, you are also more likely to miss some true positive results, because they will not be able to meet this more strict cutoff. So if you have a very small sample, maybe it's better not to use a more strict significance level or a correction for multiple comparisons. But if your sample is large enough, it probably makes sense to protect yourself against false positives by using a more strict cutoff. This way you will not get results that are purely statistical artifacts, such as this brain activation in a dead salmon. Another potential problem that is a potential pitfall when we perform correlation analysis are distributions. If your distribution is perfectly normal, if it's bivariate normal, it's a nice, beautiful ellipse, you have no problem. But if your distribution is not perfectly normal, or you have some outliers, your estimate of correlation can be biased. And if your sample is very small, this bias can be actually quite substantial. Like here, for example, you can see that this correlation is 0.7. It's very strong, but this sample is very small. It's something like 15 points. So just the presence of a single outlier, just the presence of a single point that does not conform for some reason or other to this regularity results in your correlation coefficient dropping from 0.7 to 0.4. Of course, if you are screening your data, if you're removing some outliers, you really need to have a good substantive basis to do it. But this suggests the importance of verifying the quality of your data. At least make sure that there are no technical mistakes, because they can ruin your correlations. And if you don't check your data, you might not know that it's the problem. The third problem that might not be so evident is the problem of reliability. In our fourth theme, we discussed the issues of psychometrics and measurement, and I hope that you remember this coefficient Cronbach's alpha, which quantifies reliability, or the proportion of variance in your test scores that can be attributed to the construct that is measured with this test. So what happens if your tests are not perfectly reliable? Your correlation starts to drop. Here on the right, I plotted the association between reliability of two measures of constructs that you are trying to correlate and the correlation that you will observe. So if your true correlation between two constructs is 0.5, fairly substantial for psychology, you will only see 0.5 in your sample if your tests are perfectly reliable. But of course, Cronbach's alpha is never equal to exactly 1. That's why your observed correlation is going to be lower. And the lower is your reliability, the lower is your observed correlation. So if your correlation is, if your reliability is only 0.5, your correlation is going to be 0.25. And if your sample is small, you risk missing this correlation. And you can use this formula to predict what is the true correlation between two constructs, r, x, dash, y dash. you can calculate it very easily. You take the observed correlation in your sample, and you take two reliabilities of tests x and y. You multiply them, and you take a square root, and you divide the true correlation by this. You divide the observed correlation by this square root, and you get an estimate of the true correlation between two constructs. This formula is called correction for attenuation or correction for unreliability. And we often use this formula when we perform meta-analytic studies, when we are trying to compare the results of different studies which used different tests with different levels of reliability. Observed correlations might differ just because of differences in the reliability of the measures used in different studies, but not because of substantive reasons. That's why we make this correction for attenuation when we are trying to compare the findings of different studies or for measures that differ in reliability. Of course, we need to be aware that it's better to use more reliable measures than less reliable ones. And also, this is the reason why whenever we publish our findings, we need to also publish the reliability of the measures of the constructs that we used. And ideally, we need to calculate this reliability based on our sample. So basically, in every good research paper, you will find, in addition to correlations, alpha or omega or some other reliability coefficient calculated in this sample. This is needed for the readers to understand how much the correlation was attenuated because of unreliability. The fourth problem that we can encounter when we calculate correlations is called aggregation bias. What is aggregation bias? When we aggregate or when we put together the data from two different subsamples, two different groups, if those groups have different mean scores on one or both variables, our estimate of correlation is going to be biased. And sometimes this correlation can even be spurious. Here this graph comes from the textbook by Andrei Nasledov, and it's artificial data. But here you have two groups, a group of males and a group of females, and you have two variables, height and hair length. So if we calculate the correlation between height and hair length in a group of males, it's going to be 0. It's not going to be significant. If we calculate the same correlation in the group of females, it's also not going to be significant. But if we pull together those groups of males and females into one sample, we will get a statistically significant correlation, because males have shorter hair and somewhat larger height. But it will not be correct to make this conclusion that individuals who are taller also have shorter hair, because this is completely explained by group differences. This association does not exist at the level of individuals. It is due to groups. And this is called aggregation bias, when we can make wrong conclusions. Another example of aggregation bias, here I have plotted data from 3 different companies. And there are 2 variables, employee IQ and employee salary. So if you take a look at this data, can we conclude that smarter employees actually earn more money? And if we only look at this sample as a single whole, we can say, well, yes, there is clearly a positive correlation between IQ and salary. And if we quantify this correlation, it would be something like 0.4, I guess, by looking at these points. So it would be fairly substantial. But if we look at the data of each individual companies, the correlation would be actually negative. So we can say that at the level of individuals, this correlation is negative. But at the level of groups, at the level of group differences, this correlation is positive. Groups where companies where people earn more, their employees have on average higher IQ. So basically, this is a tricky situation which you can face in educational research, in cross-cultural research, when you pull together data from several groups. You need to be aware that the differences between the groups might not be the same as the differences between individuals. And you need to consider the effects for groups and for individuals separately. The easiest way to do it is to calculate correlations for each group individually and calculate correlations for mean scores of these groups. And then you will see the differences for within group and between group effects. But of course, you can also apply a more complicated statistical model, like a multi-level model, where you can actually separate within group variance and between group variance, and you can see separately the correlations and covariances. So if you have hierarchically structured data where individuals form homogeneous subgroups, you need to be wary of this potential aggregation bias. And whenever you pull together data from two different groups, make sure that those groups are not substantially different, or better, calculate correlations and calculate mean scores for each group separately. Compare them. If there are any differences, can you really pull those groups together? If you really want to pull those groups together and you want to get rid of group differences, sometimes it makes sense to convert the scores on all variables to z-scores within each group, and then you can safely pull them. So when you deal with this type of data, you need to be very careful about the possibility of this aggregation bias. And the good news is, don't worry, this is not real data plotted on this graph. So hopefully the association within each company between IQ and salary should also be positive. And finally, the third problem, or the fifth problem, the final problem that we are considering, is called the third variable problem. If you remember, the association between ice cream sales and shark attacks was caused by a third variable, which was temperature, which resulted in people swimming more and people eating ice cream more. And this is a very common situation in research. This example comes from some textbook. And you can see that if you calculate the correlation between the amount of damage caused by a fire and the number of firemen or fire trucks who participated in extinguishing this fire, you will see a positive correlation. Now, if you have data for this third variable, which is the size of fire, which explains why there are more firemen and why the fire was more devastating, you can control for this third variable and see if the correlation between these two variables remains after adjusting for this third variable. Unfortunately, if you don't have data on this third variable, then you have a problem, because you can never be sure whether this correlation is a true correlation or a spurious correlation. You will see that there is a positive association, and you will start making all kinds of interpretations. Maybe when there are more firemen at the fire, they intervene with each other and they actually prevent each other from working efficiently. This is the kind of conclusion that you can make. But unfortunately, the first reviewer that you will encounter will say, maybe there is an alternative explanation, the size of the fire. And if you don't have data on the size of the fire, the reviewer will say, oh, this is a rubbish study. No conclusions can be made whatsoever, because this plausible alternative explanation has not been controlled. But if you have this data for the third variable, you can try controlling for it statistically. There are different ways you can control statistically. The easiest way, if you just have three variables, you can calculate what is called partial correlation. It is correlation between two variables after taking out their shared variance with the third variable, which might be their common cause. And this formula is very simple. For example, this example comes from Nasledov's textbook. where there is a group of children, and for this group of children, for each child, we have the child's IQ, the size of shoe, and we see that correlation between IQ and the size of shoe is actually quite substantial, 0.42. So should people on the basketball team get Nobel Prizes? Well, probably not, because there is a third variable, which is an alternative explanation, the age of children, which correlates both with IQ and with the size of the shoe. And if we take these three correlation coefficients and put them into this formula, we will see that the partial correlation between IQ and the size of the shoe after controlling for child's age or after partialing out the shared variance with age, the remaining partial correlation is 0, which means that there is no association between IQ and the size of shoe. Now, this is the simplest possible example of statistical control. Of course, normally we have many more variables than 3, and we apply more complex statistical models like regression or some kind of path analysis. That's why we don't really calculate those partial correlations by hands. Our statistical software does it for us. But I just put this formula here for you to understand this logic. So we have seen 5 potential sources of problems that we can encounter when we conduct correlational studies. And regardless of the statistical model that we use, even if it's not correlational analysis, we still can suffer from the problem of multiple comparisons, non-normal distributions, low reliabilities, aggregation bias, and the third variable problem. So when you analyze your data, when you conduct your correlational studies, just be aware of these possibilities which can bias your findings. And now that we are armed with this knowledge, we can take a quick look at potential designs for correlational studies. What kind of correlational studies can we conduct?